Hey guys, it's Mr. Bringle, and today we are going to talk about gravity and how that plays into our unit on forces. So to start off here, we'll just talk about what gravity actually is. It's a force that attracts a body toward the center of the earth or toward any other physical body that has mass. So we know that gravity keeps us here on the earth. And on other planets, it would be a little bit different, but there's still going to be gravity on other planets. There might be more or less. We'll talk about that here in a minute. And, you know, there's gravitational attraction between really massive objects like the sun and the planets, the earth and the moon, things like that. So kind of skipping ahead here, but the greater an object's mass, the stronger the gravitational force on it. So gravity really depends on the mass of an object and the distance between those two objects. There's an equation that explains this. We don't need to necessarily get into that. But what I do want to talk about is the difference between mass and weight. So these two things are very commonly mixed up. And your mass, every object has mass, and it's essentially a measurement of how much space does that object take up. So your mass won't change whether you're here or on the moon, right? You take up the same amount of space here versus on the moon. However, weight, on the other hand, weight is a force, and we actually use mass to calculate weight. And we multiply it by, just like our equation, F equals ma, right? F equals ma. A force is a mass times an acceleration. Well, here on Earth, the acceleration that's caused by gravity is 10 meters per second squared. So if you took your mass and multiplied it by 10 meters per second squared, it's actually 9.81 meters per second squared, but to make it easy, we'll say 10. That would give you your weight. So we'll want to keep those things straight, because while your mass would not change whether you were here or on the moon, your weight would change, because the acceleration due to gravity would be different on the moon than it is here. And that's evidenced by, if you've ever seen a video of somebody walking on the moon, they sort of are floating, right? We don't behave like that here on Earth, because the acceleration due to gravity is greater here on the Earth than it is on the moon. Now, I would like for you guys to watch this video here. I have linked this Google Slides presentation on Canvas, and this is a really cool video. It's definitely worth the watch, so you guys should check that out, but I won't be playing it on here. Now, projectile motion is one of my favorite topics, and objects, when you've seen when you throw something in the air and it doesn't continue on in a straight line, it is going to come back down to Earth, right? And it doesn't do so in a straight line either. It curves down to the surface, right? So to explain this, what we actually have to do here is we've got to separate the horizontal and the vertical motion. We have to think about them independently, and then when we combine the two, we can follow an object's path as it's thrown through the air. So to help explain this, what I'm going to do is I'm going to switch over here to something that I like to use in physics. This is just a diagram that shows a cannonball, and really what I want you to focus on right now, just to start with, is just the horizontal motion of the cannonball. Okay, so let's imagine we're in outer space, we shoot this cannonball, and because there's no force that opposes the motion of that cannonball, it will continue on in a straight line at a constant velocity until the end of time. So you can see here that after 1 second, the object is, it doesn't matter how far away it is, but it's the same distance each second, right? Because it's traveling at a constant velocity. So that's how the cannonball would behave if we just shot it straight horizontally in outer space. Now let's look at what would happen if you just dropped the cannonball here on Earth, right? So you know that when something's dropped on Earth, the object is going to accelerate. Okay, so that's evidenced by this motion right here. Okay, we're seeing that the object is speeding up as it goes down. It's going further and further each second, right? And that's due to the acceleration due to gravity. Well, if we were to take the object's position horizontally at 1 second, which would be right here, and then look at 1 second if it had just been dropped straight down, we can trace this line straight over here, and this dot is where the object would be after 1 second. Now we can do that with 2 seconds as well. We come down from 2 seconds here, we go over from 2 seconds on the vertical motion, and here's the object's position at 2 seconds. We can continue to do this by tracing 3 seconds from vertical and horizontal motion, and we find that the object would be right there at 3 seconds, and then at 4 seconds the object's location would be roughly right here. I'm having trouble drawing straight lines. And at 5 seconds the object would be somewhere right here. Well, now let's sort of connect the dots here. If we follow this path from the original position, look at that, it makes a curved line. That is the actual path that cannonball would follow if it was fired on Earth. So again, it's got to be a combination of the horizontal and the vertical motion to figure out where this object would actually go if it was thrown on Earth. Let's head back to the PowerPoint here. So if I'm moving too fast for you to fill in the blanks, just remember that I have posted this on Canvas, and you can go on there and fill in the blanks on your note sheet at your leisure. Moving on here, the last thing that we'll talk about today is centripetal force. So the word centripetal means toward the center, and so you can imagine that centripetal acceleration and centripetal force are talking about an acceleration or a force that's acting toward the center of a path, and in this case, if we're talking about circular paths, toward the center of a circular path. And got this, maybe you have ridden one of these rides before, the big swings at like Kings Island or the fair or something like that. That object, you're being swung around in a circle. There's a lot of centripetal force and acceleration involved with that ride. So the next time you go to the amusement park, you should be thinking about physics. Okay. So I do want you to answer this question: what causes a projectile's path to be curved? The answer to that will be on the top of your straw rockets page, but try to come up with the answer before you look at that. Now, as for the straw rockets, so we are going to build straw rockets, and we will launch them and see how far we can get them to go. You are going to design 2 different rockets. They have to be different. And you need to sketch for me what they are going to look like in the 2 boxes on the page that goes into your notebook. You'll put your notes on the right side. You'll put your straw rocket page on the left side. So you need to figure out a fin shape for your rocket. You have to have fins on it, a minimum of 2 fins, but you can do more. You could do 4, you can do 8 fins, whatever you'd like to do. The length of your rocket, which would just be the length of the straw, you are allowed to change that. You can cut the straw off. Don't make it too short, otherwise it won't work on the apparatus that we use to launch them. So I would say like at least an inch, maybe a little bit more than that in terms of length. Or you can leave it the same. You don't have to cut it at all. And then you also are going to need to make a nose cone, which we'll use a little bit of modeling clay for that. You've got to make sure that the modeling clay completely covers up the hole at the end of the straw. Otherwise, when we go to launch it, we're basically just going to shoot air through the rocket. It won't launch if there is a leak, and so you want to make sure that that's covered. You also want to make sure that you don't put too much clay on the end, because if you weight it too much, it's just going to basically launch and fall straight down. So you'll want to find a good balance of how much clay to put on for your cone. So you need to come up with 2 designs, and you need to draw them into your notebook. All right, have a great class, guys.